Let's discuss average rate of change. In the past, I expect you may have seen the formula for slope. y2 minus y1 over x2 minus x1. If I give you a couple of points on a line, that's something we use to calculate its tilt. But if I give you the function f of x on some closed interval from a to b, I could calculate the slope, or what we often call the difference quotient of f of x on that interval. Let the words guide you. It's not something brand new you need to remember. So f of b minus f of a over b minus a, that's what we call the difference quotient. And to be specific, difference quotient of f of x on this closed interval from a to b. You wouldn't expect that value to always be the same. I'm sure there are some instances where it would be, but you can't always be guaranteed that if you switch from, say, an interval from 0 to 1 to an interval from 2 to 5, that you would get the exact same average rate of change. So my goal, as we're moving forward, is to get a little practice here. We won't be able to calculate the difference quotient for a couple different functions on some given intervals. And let's start with a quadratic. Let's say we're going to let f of x equal x squared plus 2x plus 3. And the interval we want to focus on is from 1 to 2. Now, if I'm asking you to calculate the difference quotient, I urge you, first thing to do is not just to jump into this formula for slope, but to get your function values. Tell me what those are off to the side. It's sort of a way to check that if you find an error in your work later, was it based on a faulty calculation? So if you plug in 2, we're going to get 11. If you plug in 1, 3, 4, 5, you get 6. So as I get ready to calculate my difference quotient, I'm going to take f of 2 minus f of 1 over 2 minus 1. In specifics, 11 minus 6 over 2 minus 1. That gets me to a value of 5 in a hurry. So I could say, and I'm always going to ask you to provide a couple different interpretations. One of these interpretations is going to be more algebraic, and the other one's going to be more geometric. So the first interpretation, I could say that the average rate of change of f of x from x equaling 1 to x equaling 2 is 5. So I'm taking my time to write all this out. I expect you to do the same as well. It's really kind of a communication piece. Are you clearly indicating that we're dealing with an average rate of change? Are you telling me what the average rate of change is pertaining to? What formula, what function? We don't always use f of x. We might use g of x. We might use some other name. And then, are you also telling me where you're measuring the change from? Where do you start? Where do you stop? Don't always expect those changes to be the same on different intervals. Okay. Another interpretation is more geometric. This has to do with what we call the slope of a secant line. Hopefully that's not a surprise, because remember, this is built on a formula for slope. So the slope of a secant line to y equaling f of x. So if we're going to talk about a secant line, we need to know what it's going to be touching, on what graph is it going to be crossing. So the slope of a secant line to y equaling f of x passing through, let's see, what were our points? 1, 6, and 2, 11. What is the slope of this line? It is 5, just like we had a moment ago with the average rate of change. So once again, let's highlight those things we don't want to miss. It's the slope of the secant line to a particular curve passing through a couple points. So all of these are really crucial pieces to interpreting it. I'm not the best artist. I don't have pictures of this right now, but I'm very good at using graphical utilities to give a picture. If you look at the resources I've posted in Blackboard, my lecture slides, I create pictures with this so that you can really see how we've got a quadratic, we've got a line passing through, a secant line passing through these 2 points, and it all kind of comes together nicely. Let me erase just here for a moment. I got one more example I want to work with you. This one will need a little room. We're going to do some trig. So what's the average rate of change of sine on the interval from pi over 6 to 3 pi over 4? This time we're going to call g of x sine x, and on the interval I just indicated to you. Let's figure out what the coordinates are. If we're going to do a difference quotient, we need to know what g of pi over 6 happens to be, as well as g of 3 pi over 4. Well, if you're at pi over 6 radians with sine, you have a value of 1/2. If you're at 3 pi over 4 radians with sine, you're going to be at 1 over the square root of 2. I recognize it's the same thing as square root of 2 over 2. Either one is fine. So if I'm going to try and calculate the difference quotient for g of x on this indicated interval, I need to take g of 3 pi over 4 minus g of pi over 6 divided by 3 pi over 4 minus pi over 6. So we're going to have to do a bit of work here with some fractions, a little bit with simplification. Let's kind of roll our sleeves up and get ready for this. So g of 3 pi over 4, 1 over radical 2 minus 1/2, that's what our numerator looks like. 3 pi over 4 minus pi over 6 in the denominator. I'm going to focus on getting some common denominators. This complex fraction, I'm going to start cleaning it up a little bit. I could think of 2 minus a radical 2 over 2 radical 2. It's not the least common denominator, so to speak, but it'll work. And then doing something similar in the bottom, I've got 18 pi minus 4 pi all over 24. Let's make sure we don't lose track of where the true numerator and the denominator happen to be. You know, when you're working with a fraction like this, I think it's easier to invert and multiply. So let's think of this as 2 minus radical 2 over 2 squared root of 2 times 24 over, we're going to get down to 14 pi. Okay. We pause for a moment there. Just to recap, we got common denominators, and then we, instead of having a big fraction, complex fraction, we multiply by reciprocal. Where do we go next? It's really about simplifying, and how far do you need to simplify? Kind of depends on what you prefer in some senses. How do you want square roots in your final answer? Where do you want to be at? Of course, we always want to shrink numbers as much as possible. I mean, 24 and 14, that becomes 12 over 7. The 2 and the 12, I can get 6. So in a hurry, I could say, hey, this is 6 times 2 minus radical 2 over 7 square root of 2 pi. I mean, that's an improvement. I really don't like that square root of 2 being in the denominator. I'd like to maybe move it around a little bit. So 7 pi was what I really want to have in the denominator. Let's kind of off to the side here and think for a moment. If you had 2 minus square root of 2 to divided by square root of 2, that would produce square root of 2 minus 1. So what I'm going to do here is just divide in that set of parentheses there, that 2 minus square root of 2, and get myself to a real kind of clean response. Maybe it isn't a decimal. I reckon there'll be plenty of engineers in my audience whenever I'm teaching this. Why don't you type that in and see what the estimate is, maybe out to 3 decimal places, 4 decimal places, depends on the context, how far you need to go out. I agree, there are times when I would do that, but right now I don't know how much I'm going to need to be accurate or how much precision I'm going to need to show. So I'm going to leave it like this until I am at a moment when I can have more directions and go exactly to what is needed. It also helps me if I'm trying to maybe see if there's another relationship, maybe there's another idea that I want to see if they're equivalent. Leaving it like this can really bring that out, where the decimal doesn't always do so. Now I got 2 more interpretations. I don't want to forget about that part. I've got a value, but what does that value mean? Well, the first thing, this represents the average rate of change. I see plenty of students say AROC, AROC. The average rate of change of g of x from x equaling pi over 6 to x equaling 3 pi over 4. That is this particular value. Give me a minute, I'm going to kind of reference that. And I could also say, we've got the algebraic look here, I could also say that this represents the slope of a secant line to the graph of y equaling g of x from x equaling, sorry, not from, so the slope of the secant line to the graph of y equaling g of x passing through. I'm going to give you a couple points. Let's see here, we've got pi over 6 comma 1/2. I'm going back to this information we had up here. And 3 pi over 4, 1 over radical 2. That is also what this quotient represents. So as we go through, there are going to be many, many times where we need to interpret our results. This is sort of a way to start practicing that. Let me know if you have any questions.